From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Ford used to have this sign hanging in their cafeteria that says, "Culture eats strategy for breakfast," right? And what they're trying to say is, you can have the best technology in the world, but the culture of the design community may or may not let you use that technology.
That was Don Godfrey. Don is a senior fellow in aerospace and Department of Defense additive strategy at SLM Solutions. He's a globally recognized authority on additive manufacturing. Don spent 14 years at Honeywell Aerospace and is recognized as the person that led the incorporation of metal 3D printing within that company. He incorporated additive manufacturing technology for Honeywell locations in China, the Czech Republic, India, Mexico, and 3 printing facilities in Phoenix, Arizona, with one being a reactive metals production facility and another being a nickel alloy production facility. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher.
All right, Don, thank you so much for joining the show today. I'm super excited for the conversation. I've seen you talk at many industry events, I think most recently at America Makes, and the knowledge that you have on the industry is unparalleled. So I think it's going to be a good conversation. So I like to start all of these episodes with a little bit of context about Don the person versus Don the additive manufacturing expert. So kind of where'd you grow up? Kind of what was kind of early days like, getting you kind of on the path towards engineering and eventually additive manufacturing?
Sure. Well, I grew up on a small farm in southern Indiana. And I'm probably equal distance between Indianapolis and Bloomington, which is the home of Indiana University. I went to Purdue, and when I left there, I took a job as a welding engineer for a company that's no longer in existence. It was Stuart Warner. We made heat exchangers. And that company has since been acquired by Meggitt out of the UK and moved out of Indy. And then I went to work for a robotics welding company as a welding engineer. And we did that for about 6 years. And I ended up going to General Motors, that was actually Allison gas turbine. And that company was acquired by Rolls-Royce Aerospace, and then Honeywell Aerospace, and now SLM. So 11 plus years at Rolls-Royce and 15 years at Honeywell Aerospace, and 2 years here.
Was there anything in particular that got you really interested in manufacturing? I mean, you had the welding background, kind of degree.
It's kind of funny, you look back on it now, but when I was really very good at welding. And when I was 16 or 17 in high school, I won like a third place national position for the James F. Lincoln Welding Foundation, right? We build these great big welded projects, and you submit them, you do all the math, and they send you a little prize and a book in the mail. And I've always liked welding because I think for 2 reasons. A, I was really good at it, and everybody I knew hated it, right? And so when I was at Purdue, the professors had me help teach these classes they were just setting up programs to help minorities and underprivileged students. And so they had this huge lab, and I got this job in this lab, and I just always liked it, right? So even though we call it 3D printing, you're welding. It's fusion welding. It might be on the micro level, but you're welding.
For sure. And so when did you kind of get your first introduction to kind of the 3D printing, the additive manufacturing as we think about it today versus the kind of traditional welding?
So I was at Honeywell, and we were on a new engine program, and there is a component that we just nicknamed the TOBI, T-O-B-I, which really is a tangential onboard injector. So when you're running air through a compressor, you're swirling it, but if you hit the combustor with swirling air, you blow the flame out. So you want to take that swirling air and straighten it out so that it hits the compressor. And we worked for a year to get these cast parts. And when we modeled our cast parts, they had 5% more flow than the CFD model said they should have. And so the turbine engineers were just having a fit. And we needed a new one. Well, that meant we need a new core die. And the casting house, we white light inspected this part to death. And the hats off to the casting house, they made it exactly to CAD file. It was perfect. It was the CFD model that was wrong. And so that same week, I was in a meeting with this guy named Greg Morris out of Morris Technologies in Cincinnati, Ohio. And this was prior to GE buying them. So this is like 2008. And I said to the team, because if we didn't have these TOBIs, the right TOBIs, this testing schedule is going to get pushed back a year, which that is never good. That is not good, especially when you've got 100 engineers on the program, right? You're going to let all these guys go. They're going to go to different programs, and you're not getting them back. So I contacted Greg, and we printed 8 of them in the next 4 weeks. And we kind of did a DOE, really, in that we printed, we knew the cast parts was letting in too much air. So we just started sizing them back, right? And then we found 3 of them, right? They matched the CFD model, but not the CAD model. But, you know, that was the saving grace, right? That's how we introduced metal printing to Honeywell Aerospace. And it saved a multi-million-dollar, really $100 million program. Just those 8 parts.
And so at this time, were you constrained at all by kind of the available materials, or kind of the,
No,
like, what were the constraints?
We knew it was 718. We knew it was 718. Okay. And it was risk, really, right? I mean, we made a few tensile specimens. We did a few metallography looks, but our back was to the wall. Either you get a TOBI in that engine in 2 months, or we let everybody go. Because if you get knocked out of Q, there's 5, 6, 7 other engine programs ready to go in your spot into those testing cells. So do or die, print it or go home. And that's what we did.
That's awesome. And so, I mean, as you kind of get the proof of concept there, I mean, it saves the program, or saves kind of the timeline at least. What's involved after that? So you get kind of, you immediately get kind of instant feedback, but you probably don't have that initial time to do what we think of kind of the full suite of qualification and
you're right.
multiple machines,
right. So,
and all of that.
So when we had a new engine, there were multiple new technologies that we're testing. So we assembled the engine and we took it out to the Santan Proving Grounds, which is about 40 miles away, 30 miles away. Fired this engine, nothing blew up, so we're good, right? And then we ended up, when you do these, we had a 737, and then on the side of the fuselage, you have a special made bracket where you hang your engine or your APU, right? And you take it up to 30,000 feet, you fire it off. The engine's not certified to lift or land a plane. So you have 2 certified engines on the plane, and then you get this thing hanging on the side that once you get above a certain altitude and away from the population, you fire it off. And I checked with Greg Morris. I checked with Hans Langer of EOS. Honeywell was the first company in the world to fly a printed 718 part, because everybody else had been screwing around with aluminum. But we did that. And that was 2008, maybe early 2009. And that was really something the team took a lot of pride in. And it opened the door for people to start talking about additive, even though there was a strong cultural resistance, because we didn't have material properties, right? We didn't have B bases, certainly, right? So we had parts, we were flying those parts, we had them in test cells, and nothing drastic happened. So everybody's anticipation started to come down. We had, because the microstructure is much smaller than what you would have with a casting, you had increased tensile strength at temperature, even at room temperature. So we felt pretty good. And then that's the reason why we chose 718 as our first material. It's kind of funny, as soon as we did that, all the space people coming down, it's like, why aren't you doing aluminum? Why aren't you doing titanium? And it's like, we're an engine company, right? We don't put aluminum on engines. But Honeywell's this huge conglomerate of satellite makers and landing gear makers. And everybody uses everything different. But our first alloy was 718.
And so that's really interesting that you almost see it in reverse a lot in kind of current additive manufacturing space. Like in this case, like you proved that you could go throw an engine component on a plane, and at 50,000 feet, nothing blew up. And so like the worst case scenario is kind of taken off the plate for all intents and purposes. And then you can kind of go back and do some of the more rigorous mechanical tests, whatever you're doing. A lot of times that I've seen other companies, and I'd love to get your perspective on this, is like they spend so much time digging into the microstructure, the mechanical properties, that they almost lose track of like, hey, is it going to be good enough? Like you can nitpick on a million different things, and parameters can change in different machines, but it's often the case that there's a very long lag in terms of qualifying a material if you come at it just on proving that the mechanical properties are sound or good enough, and no one can ever tell you what that is.
That's true. The 2 greatest impediments to accepting additive manufacturing are the lack of material property data and culture. Right. So I can remember printing parts, and the turbines group wanted to do all this testing on, and I asked the simple question, well, how does casting stack up to this testing? And the answer was, well, we never did that, right? Because that technology didn't exist 20 years ago, right? Well, then why are you doing it now? Because it just seems that what you're doing is adding on more and more requirements that you would not add on a casting. Now, granted, we've been using castings for 50 years, but you don't know what the results of those tests would be if you did a casting. So therefore, you don't know what's good or bad, right? In my mind, if you're replacing a casting, you have to be better. The FAA has specifically say You have to be good as or better than what you're replacing. So because of the microstructure, you're much better at tensile, right? Much better than a casting. You have the same oxidation resistance. You have improved creep. You have improved HCF. But it's like testing after testing. You know, there are 2 books on this very topic. In fact, if you go back into the 1980s, now, Ford used to have this sign hanging in their cafeteria that says, "Culture eats strategy for breakfast," right? And what they're trying to say is, you can have the best technology in the world, but the culture of the design community may or may not let you use that technology. So Condoleezza Rice wrote a book, she co-authored a book called Political Risk. And the other book I thought was fascinating on this very topic was the Space Barons, where it talks about the creation and emergence of SpaceX, Blue Origin, Virgin Galactic, yada, yada, yada. And Condoleezza Rice's book focused a lot on corporations who are afraid of new technologies, because if it doesn't go well, it could hinder their employment with the company. You know, and it's just, in my role, even at Honeywell, I was working to develop the supply chain for additive. You go into these space companies in California, for example, and you're going to see nobody over 35 years old. And you're going to see additive machine after additive machine. And you don't count them 1, 2, 3, 4. You count them 10, 20, 30, 40, right? But if you go into some of the aerospace companies where the engineering age is much older, it's like, oh, there's another barrier you got to go over, right? People are afraid to make a decision, even if it's a better product. Culture always wins, right? And it's in proving it to them metallurgically, it's not always good enough.
Yeah. It's just one more excuse that they could use to delay it or not make the decision, right? We need more testing. We need more. It's uncertain.
I talk to young people at various companies, and they're like, because they have a little bit of additive, and this is really true for all the OEMs, you become hot property in the job market, right? If you know additive, you're going to get a job. And the question they have to ask is, do you want to be employed in an area where you have the latest and greatest propulsion technology, or do you want to be employed making spare parts for 30-year-old engines? Because that's really where we are. I mean, right now, the hypersonics market, the space market, it's hard to keep up with it. They're growing so fast.
Yeah. And so you mentioned kind of as one of your roles at Honeywell, you were kind of tasked with building out the supply chain. So can you tell the audience a little bit about, like, what does that mean? Like, what did your day-to-day look like in terms of what you were doing in that position?
Okay, so let's kind of take a look at just the value chain of an additive manufacturing process, right? Every powder company in the world will tell you, if you buy their powder, you can print XYZ, right? That is the biggest hunk of baloney ever created. So what you're looking for when you certify a powder company is, first of all, can it even print in your machine? And I would say 50% yes and 50% no. And it all deals with air classification technology, because the fines that typically would be sold off to the metal injection market can find its way into your powder. And these fines act like a glue. right? So it won't spread. So if a company doesn't have air classification, you don't want to be messing with that powder. Now, what you want to know when you do a B-basis, and you really want the voice of the supply chain, right? So let's say you pick a company, whoever that might be, Tecna, AP&C, Praxair, you pick it, right? What you want to know over a series of orders, are they sending you the exact same powder? Do you have the same powder size distribution? Do you have the same morphology? Do you have the same chemistry? And one of the bad habits you have in the powder market is that they have a SDS sheet that they printed off in January, stick a bunch of them in the drawer, and they just stick it in the box with the powder, right? If you take 100 grams of that powder and you send it out to a testing lab and have them test the chemistry in the PSD, it'll vary from order to order to order to order. So what you want to know is the powder that you order in January the same powder you get when you order it in August and then December, right? They'll tell you it is, and in a lot of cases, it's going to be close, but it changes, right? So, and when you're with a big company, metallurgists sometimes like to, and they did this in the casting era. They like to they'll take the chemistry by percentage of weight, and they'll shift maybe the percentage of aluminum or maybe the percentage of titanium. It still falls under the chemistry of that alloy, but now you've got a unique alloy because maybe they say nothing more than 200 parts per million oxygen. But the standard spec may say it's 300 parts per million. Some engineer, some metallurgist along some decade ago said, we're going to have 200 parts per million of oxygen. Well, are you really getting that? Are you checking it? Are you measuring it? Because that piece of paper is only checking a box that they sent you a material safety data sheet, right? Unless you measure it, you don't know. So that's company one. But a lot of companies, because of supply chain issues, want more than one supplier, which makes a lot of sense, right? You want to do that. Well, now you've opened the door up to another variable. How do they stack up? And if nobody wants to do three, you typically will do two, but if you do three, you have to ask yourself and prove with empirical data, what is the worst chemistry of those mixes? Say you get 30 different mixes of powder. What is the worst chemistry? And then what are the mechanical properties associated with that worst chemistry? It could still be in spec, but we've shifted elements now, right? And so that's what you have to prove to the FAA and to EASA, is that given the voice of the supply chain, you're going to get over 2 years, 3 years, 4 years, heats of powder that have a chemistry over here and heats of powder that have a chemistry over here. How does that influence the life of the part that you just printed? And you have to know that answer. It's expensive to do that testing. Typically, once you qualify a machine, when the smart way about it is to print 2 or 3 or 4 tensile specimens or HCF specimens each time you print a part. And that helps you qualify that part. But more importantly, it builds you the database that you can answer that very question. So you have to have, either you test it in-house, you can do that, but governing agencies like to see that NADCAP stamp on it, right? And even though you may have a whole room full of PhDs that do everything perfectly. You don't have that NADCAP stamp on it. So you send 100 grams out to wherever, Westmoreland, Element, there are 100 labs, right, you can go to. But you need some sort of documentation. And then you, over time, you build your proof, your database. So, then you do that. So that's how you qualify the powder, right? And that usually involves sending metallurgists out to the powder plant or plants, and you audit them. And you audit them every, it's up to you, right? Every year, certainly every 2 years. And then that's kind of how you do the powder. Then you got to qualify your machine, right? And you do that through a series of tests. And then you have to qualify the process. So now we get back to how does the process vary over time, right? So it has to be fixed when you start it fixed. So the variability is going to come from your powder. Do you have moisture in your argon? How dry is it? Because if you're printing things that are sensitive to humidity, it matters. Then what kind of testing are you going to do? Then where do you heat treat it, right? That heat treating is the worst thing in the world. I've sent aluminum to companies, and the people on the floor weren't watching. They jacked it up to 1900 degrees. You get back 2 puddles. I sent titanium to a company, and they called me after a month. We were upset. It was late. And they said, "Oh, we burnt the building down." And I didn't believe him. I got on the internet, and they literally did burn the building down. So that cost me 8 weeks of schedule. I had to build them again. So you got to qualify that, usually to a standard. And then how are you going to machine it? How are you going to inspect it? All of that has to be auditable and repeatable. And you don't even start in the supply chain. You don't even start unless those companies are AS 9100, ISO 9000, NADCAP approved companies. Because there are so many variables, you have to deal with people who understand what it takes to get something approved by the FAA. I have had a lot of companies tell me that they're going to buy a machine and start printing stuff. And that is the worst thing you can do. I asked the guy once why he bought the 2 machines he did. And he says, "Because I own stock in the company." They are, yeah, whatever. Okay. Yeah. So, yeah, it's got to be, it's a science. It really is a science.
And so kind of, I recall the conversation, I think you're on a panel at one of the American Makes event out in Utah. Mm-hmm. And one of the things that came up was this idea. So you laid out kind of a great kind of workflow of qualifying the powder, the process, the post-processing, mm-hmm. the part. The early part of that, where it's the machine and the material, everybody's got to do that, right? It's not just Honeywell, right. It's not just Lockheed. And so it seems like the winners in this is Westmoreland Element getting all the same test bars over and over again, right? Yeah. Every year. And so how is that? Do you think that's the status quo? Is that kind of how we should keep approaching that everyone kind of views that as a secret sauce, or is enough of that generic over time that there's a need for some cumulative, or like at some point it becomes more shared knowledge, right? Baseline knowledge at least.
So there's 2 avenues to that answer. One, I would hope that with this announcement by President Biden that we're going to do this AEM program, I hope somebody is smart enough to realize, let's go take a few $1 million and develop B bases for multiple alloys and give it to American industry, give it to NIST, give it to ASTM, give it to ASME, and just give it to them for free. because without it, you're dead in the water. Now, when you qualify a machine, let's say you qualify for 718, whatever else it is, and you're printing part X, you do not have to requalify that machine again if you want to print part Y, because you now have a machine that's qualified, and by printing, by qualifying the process, as long as it's the same material, you can accept material properties and process by similarity. Now, you still got to test it, right? The FAA is not going to let you put a part on that you didn't test, right? So you can cut it up and look at microstructure. You can cut specimens out of it and bolt it on an engine. But it's pennies. The first part is always the most expensive, right? Always. But as long as you don't change material, and let's say you're doing brackets, you can do a family of brackets. Once you bit the dust for that first one, it's easy to get the others done in comparison. It's when if you're printing part X in 718 and you for some reason want to go to tie 64, you're going through the whole process again, right? Because you got a different atomizer, different powder, probably a different supplier, different machine settings. You're starting over. So once you qualify, the first thing you want to do is find a family of parts and then just capitalize on your expenditures, your expenses. So ballpark, right? If you're going to get the basis, you're looking at 700,000 to 1.5 million. So typically, when you look at the MMPDS requirements, it's focused on tinsel. And so that opens up the door immediately to, well, what about these other tests? Do I have to do 300 of these tests also? And at what temperature? Because since you don't mention the temperature, everybody defaults to room temperature. They're not stupid, right? It's $120 to do a room temperature test. But if you're doing, like we're working with NASA right now, and they want to test titanium in the cryogenic zone. Well, that's not $100. I can guarantee you, right? When you go to 200 below zero, or if you're doing a new nickel alloy and you want to test at 1700 degrees, it gets expensive. And when you look at a creep test, for example, even a room temperature creep test starts at $2,000 per specimen. The question is, how many are you going to do? And the answer always is, and I don't want to be smart aleck about it, but whose budget are you using? Because if you're using the engineering budget, 10 tests ought to be enough. If engineers find out you're using somebody else's budget, it'll be 50. So when you do that, you do room temperature, but how, depending on the alloy, depends on what temperature heights are you going to, or what temperature lows, right? It's just so expensive to get these tests done. And so that's why I think it would be great. I mean, if I were king for the day, I would tell NIST, the National Institute for Standards and Technology, here's $100 million. Go out and get all this done and give it to America. That's what needs to be done, because when companies spend this type of money, they immediately, and rightfully so, they immediately see it as their IP. They spent $2 million to develop this. Why should they share it?
Yeah, absolutely.
And they don't.
Yeah.
Okay.
Yeah, because someone else has to go and repeat it, right?
Right.
So, So, I mean, you spent a number of years at Honeywell, kind of you're now at SLM. So what was that transition like going from essentially an end user kind of overseeing kind of an additive supply chain to a machine manufacturer?
It was a kind of a odd transition, really. Boeing came to us and said, we're not going to accept any more engine deliveries this calendar year. And that was April. And everybody just went like, oh, right. And, one wave of layoffs, the next wave of layoffs. And I'm sitting there thinking, 70 patents, I should be safe. But I wasn't, right? The whole AM team got nailed. So I had 4 job offers in the first 3 weeks. I was interviewing 2 days later. I knew where I was going to go. Once you have these skill sets, you're employable anywhere in the world. And so it is different. Not only is it you're now working for an OEM, you are working for an organization that is a different culture, right? It's not an American organization, it's a German organization. And there are differences. Now, we have our corporate offices for North America in Michigan, but every day you're dealing with people that are 10,000 miles away, right? Meetings start sometimes 5 a.m., right? But it's a good company. It's a good fit. And sometimes you read emails and DMs that they send you and think like, is that what I think it means? You got to read things 2 or 3 times before you react. I've told them and they've listened the importance of finding material properties and getting them documented before you ship a machine out. We now have this huge database, and we pull tensile specimens on every machine before it ships out the door. And we didn't used to do that, right? And I can tell by looking at those tensile specimens, is that machine meeting our quality levels or is it not? And if it's not, it better not leave that plant, right? So I think I've had that influence, and SLM is unique, right? Because I come to them with 25 years of aerospace experience, 26, 27, whatever the number is, right? Where I spent 10 years putting these systems, additive systems, into production and getting parts qualified to FAA requirements. And I find myself working with companies around North America doing the same thing I did at Honeywell, only I'm wearing the SLM badge, right? So I'm like one of their, I help them get over some of the hurdles and tell them, you need to do X, Y, or Z. And our CEO asked that I write a document on how to qualify the machine. And I went back to them. Basically, all I did was document what we did for the FAA. And I remember the public relations people thought, they said to me, we thought this would be 500 words, right? And so we worked for the next 3 weeks to get it down to 13 pages, something that we could publish on the internet and give to our customers to show them what you have to do to, after you get the machine installed, to how do you qualify that machine and how do you qualify that process. So it's different, right? I mean, I bring a different perspective to them, and you realize no other company is doing that. No other a lot of people will sell you a machine. No one knows how to help you get that machine qualified. And that, believe it or not, buying $1 million machine is probably not the most expensive element of this process. Right? It's how much are you going to test? Who are the flight safety engineers? Who are the FAA representatives in your company? Because without their signature, nothing goes on a plane. Nothing. Right? And so they have to be an integral part of any program that you're going to do to put something on commercial aviation. Now, the Navy and the Air Force, they may or may not have stringent requirements. They're not going to put crap on their plane. But if it's a dual engine or it's a dual application part, the FAA has priority by default. It is their responsibility. But if you're printing something for SpaceX, Blue Origin, US Navy, those customers decide what is good or bad.
And so it sounds like on a kind of typical day, you're talking to a lot of customers, you're talking and have a lot of internal conversations about machines and the process, and then kind of doing you're at a conference now, so kind of doing right. Business development. So it sounds like a busy day on any given day.
Yeah. So this is Wednesday, right? So Monday I had a meeting with NASA in Huntsville. Tuesday a meeting with NASA Glenn in Ohio. Today another NASA meeting. General Motors, because General Motors got the contract from NASA to build a lunar rover, which is really a pretty cool project. That's in the public domain. You can Google it. So we're talking about unique alloys that the NASA people are developing, and we're talking about unique applications, right? So it's kind of fun, right? So I've collaborated with other companies in the past on the development of F-357. And so there were 3 companies that put money in the pot to go develop this. And one company didn't want to do low cycle fatigue testing. They only wanted to do high cycle fatigue testing because they were making satellites. And they said, we only have to go 15 minutes. You get it in orbit, we're done. And another company made missiles. And they said, we don't care about LCF because 2 minutes after we hit the launch button, it doesn't exist anymore, right? But in our case, where you're making components for aviation applications, that part may be there 30 years, right? So each of the 3 companies had different testing requirements. And the same is true today with the NASA programs we're doing. Some companies want to do room temperature tests, but if you're building a lunar rover, what happens to the thermal stresses of that part if at 8 o'clock it's in minus 200 degrees F and at 12 o'clock it's plus 200 degrees F, right? What happens to that over time? And the only way to really know that is to test and test and test and test and test some more.
So last question, I mean, upon reflection of your own career and kind of what you're seeing on a day-to-day basis in the additive space today, what advice would you give someone on the other side of the spectrum, just starting their career out, kind of evaluating manufacturing as a career path, maybe engineering or your track on the welding side? Any kind of reflections or learnings that you could have taken away from your time at Honeywell and aerospace and SLM?
Sure. One is, if you want to work in this field, we always focused on, when we were hiring interns, you always focus on young engineers that knew how to use CAD use it well, right? That is a very important element of the technology, because if you don't know how to do it, you're dependent on the guy next to you to do your work, and that never. You have to be a good communicator, right? You can't be introverted. It's so much to learn so fast that you're relying on one another. And a lot of the interns we brought in, we didn't hire, because for us, work ethic is everything, right? I don't care how smart you are. If you're not willing to get out there and get it done, you're of little value. We, yeah, you might have a master's in engineering or a PhD, but the best way to teach an engineer on how to design with minimal supports is let them go out on the floor and remove the supports off the design they just created, right? You learn pretty quick that you can take 30 minutes out of this process by doing your design differently. We want people who are willing to build the machine, put the base plate in, the build plate, take the powder out. Now, that's not going to be your job all the time, but you shouldn't complain about it. Go out and put the safety gear on and get this done, because somebody's got to do it. And if you're not willing to do it, then there's a problem. So cooperation, work ethic, and no CAD really well. That puts you way up the level of everybody else.
Fantastic. Well, Don, thank you so much for joining the show today. A lot of great insight as always, and look forward to seeing you at an upcoming event.
Yep, I'll be there probably. But thank you for inviting SLM to be part of this. It was great. Thank you for inviting me.
Absolutely.
All right.